In the previous video, you guys learned about magnetic dipole and magnetic dipole moment, right? So now what we'll do is, so you have a very simple derivation. That is, suppose let's say you have a bar magnet, alright? Now what is the magnetic field due to the dipole in an axial point? Okay, so this is how the figure looks like. Okay, it's just an axial point, alright? Now if you carefully look at the figure, see there are two poles, north pole and south pole, correct? Now both the poles at that particular point, let's say some point P we are taking in the axial line, okay, and then you have two poles, north pole and south pole, right? Now north pole gives one magnetic field and south pole gives one more magnetic field, okay. Now whatever distance we are taking will always be from the center of the dipole, correct? So let's say the distance from the point P to the center of the dipole, let it be r, okay, and then the total length of the dipole is 2l, so that is l and l, okay. See, now what we have is we need to figure out the magnetic field at the point P, correct? So like I told before, again I'm repeating this, there are two magnetic fields, okay, one from the north pole in this direction, one from the south pole in this direction. Again I'm repeating this, all right. Now why I'm stressing on this particular point? Because you need to subtract the magnetic fields at point P, okay, we need to subtract it. So B1 is equal to mu naught by 4 pi into m divided by np square, correct? Because np is the distance. Now same thing from S, that is from south pole, becomes B2 is equal to mu naught divided by 4 pi into m divided by sp square, okay. So you have these two. Now what is np distance? If you look at the figure, so O to P is r and then n to P we need to figure out, correct? Now don't you think it's nothing but r minus l, because r minus this particular length is l. Now same thing, sp becomes r plus l, correct? So you have np square sp square. Now substitute that. Now the net magnetic field at point P, B is equal to B1 minus B2, because B1 is closer to P, correct? So B1 is more in magnitude. So you will get this as mu naught by 4 pi into m divided by np square is nothing but r minus l whole square minus mu naught by 4 pi into m by r plus l whole square, right? Now you have many things common, so you take it outside. So you have mu naught by 4 pi into m as common, so you'll get this as 1 by r minus l whole square minus 1 by r plus l whole square, okay. Now take the LCM, you'll get this as r plus l whole square minus r minus l whole square divided by r plus l into r minus l whole square, okay. Now in the numerator, if you expand using the identity a plus b whole square and a minus b whole square, so if you simplify, you will get the answer as 4rl, okay. So 4rl by r square minus l square whole square, okay. So if you combine everything together, you have b is equal to mu naught by 4 pi 4rlm divided by r square minus l square whole square, correct? See, in the numerator you have 4rlm, correct? Now what we'll do, we'll split it as 2l into m into r into 2, okay. So we'll split it. Now if you look at this, magnetic moment is given by m into 2l, correct? Right? So you substitute that here. So if you substitute that here, so what you will end up is, you will end up with b is equal to mu naught by 4 pi into 2mr divided by r square minus l square whole square, okay. So I repeat this again. So you have b is equal to mu naught by 4 pi into 2mr divided by r square minus l square whole square. Now this is the magnitude of the magnetic field at a point in the axial plane of a magnet. Okay, now obviously the SI unit becomes Tesla. All right, now go through this derivation again. All right, okay, because this derivation is quite important from board perspective.